Let me help you ace your Precalculus Exam 1 by solving Unit 4 questions about exponential and logarithmic functions. Let's start by making sure we understand the relationship between logarithmic and exponential functions. Problem 1 says, given real numbers b and x that are positive, with b not equal to 1 because that's not interesting, describe the meaning of log base b of x. This symbol is described as log base b of x. Also, what are the fundamental algebraic properties of log base b of x? And explain why these properties are true. I'm not going to do full proofs, but I will give verbal explanations and I'll write equations. So what is log base b of x? This is an exponent that has a certain property. It's the number that b, the base, must be raised to, the number that b must be raised to get the number that's in the parentheses there, x. The number that b must be raised to get the number x. This should beg a question in your mind right away. How do you know there is such a number? Well, we'll talk about that as time goes by here. In other words, based on this definition, you can write down one of these fundamental algebraic properties right away. If I take the number b and raise it to the log base b of x power, b raised to the log base b of x power, I have to get x. Maybe a particular example will help. What is log base 2 of 8, for example? This entire symbol represents one number. It represents the number that 2 must be raised to in order to get 8. Well, a little bit of experimentation should reveal that you've got to raise 2 to the 3rd power to get 8. So therefore, that means this number, log base 2 of 8, must equal 3. That's the exponent 2 must be raised to get 8. As another example, what's log base 2 of the square root of 2? What number, this entire symbol represents again one number, should I raise 2 to get square root of 2? Lots of 2's in there. A little bit of thought reveals that the answer is 1/2. Why? Because 2 to the 1/2 by definition, this is a definition, is square root of 2. Now you can ask why that definition makes sense. That's beyond the scope of what we're doing here, but you should know that's true. One more example with log base 2. What's log base 2 of, say, 1/16? This represents one number. What number do I have to raise the number 2 to in order to get 1/16? That's a little bit confusing perhaps. If you know what it means to raise a number to a negative power, you quickly see the answer is -4 because 2 to the -4 by definition is 1 over 2 to the positive 4th, and 2 to the positive 4 is 16, giving us 1/16 when we raise 2 to the -4 power. Therefore, this logarithm is -4. But anyway, those are examples of this one property right here, illustrating the idea that, again, this is the number that b must be raised to in order to get x. So there again is one fundamental property. Another fundamental property essentially switches around the exponentiation and the logarithmic taking. What is log base b of b to the x? We can still use this definition to help us figure it out. This entire expression represents one number. It's the number that the base b must be raised to get the thing inside the parentheses, b to the x. I guess you'd have to raise b to the x power to get b to the x. Yeah, that's true. This is another fundamental property of logarithms. Log base b of b to the x equals x. It's like the logarithmic function here and the exponentiation cancel each other out. In fact, they are inverse functions of each other. In the situation where b is positive and not equal to 1, if f of x is b to the x, then its inverse function, f inverse of x, will be log base b of x. Will f have an inverse? Will it be a one-to-one function? Well, if b is bigger than 1, it's exponential growth. That's if b is bigger than 1. If b is between 0 and 1, it's exponential decay. In both of those cases, this graph passes the horizontal line test. No horizontal line goes through it more than once. It is a one-to-one function. It's got an inverse function, and that inverse function would be log base b of x. if we use the reflection property of inverse functions, when b is bigger than 1, I have to reflect this graph across this red line. This is y equals x here. And I would get a graph about like this. That's going to be f inverse when b is bigger than 1. And if b is less than or between 0 and 1, I have to reflect this graph across that line. That's a little difficult to do. It's maybe good to switch your paper around like this, turn it. I'm trying to reflect this graph across this line. Again, it's kind of tricky. Something about like this is what it would look like. That's what the log base b of x graph would look like if b is between 0 and 1. Though we almost always think about cases where b is bigger than 1. So that's the main kind of graph that we think about. What are some other properties? Well, maybe you've learned them. Let me write them down. Log base b of a product, say x times y. When I write xy, it means x times y. The log of a product is the sum of the logs. This is another fundamental property of logarithms. It is assumed here, by the way, in all this, when I think about the log of a number, that, as I said at the beginning, that the input for this function is positive. So x and y both need to be positive for this side to make sense. Technically, if x and y were both negative, this side could make sense. But if we want this to be true, x and y both need to be positive so that the right side makes sense. That's one fundamental property of logarithms, but why is it true? You should do a proof. I'm not going to do a full proof. Again, I'm just going to write down an equation and explain it. The key thing to realize is that every property of logarithms is based on a property of exponents. Start with the right side of this equation that we're trying to prove is true. It's the sum of two things. Make that the exponent of the b. And why is that suggestive? Why do we want to think about that? The reason is because there's a property of exponents that says when you take a number and raise it to the sum of two numbers, then that original base, that thing that you get is equal to the original base to the first number times the original base to the second number. In this case, b to this sum is b to the first power times b to that second power. Why does that work? It's a property of exponents. It makes the most sense when these numbers happen to be positive integers. I'll let you think about that with examples. Maybe you even want to try a general proof. So that's a fundamental property. And then think about using this property, both here and here. That's x times y, or just xy if you prefer. And then use this property again. Why? Because I'm trying to show these two things are equal. I've got the right side in this exponent. If I can show that I get b to the left side, then the exponents must be equal. This property must be true. And that's true because, once again, I'm using this property here, but now with x replaced by x times y. That's supposed to be a log there, a little typo there. Log, log base b of x times y. Technically speaking, to now get to the final conclusion that these exponents must be equal, we also do need the fact that b to the x power, when b is bigger than 1 or between 0 and 1, is a one-to-one function. We've got these two outputs being the same, therefore the inputs must be the same. That would allow us to conclude this. The other two main properties are that the log of a quotient, x divided by y, is the difference of the logs. And there's also a property about raising the input for the logarithmic function to a power and see what happens with that. To see why this is true, do the same kind of thing we did over here, but now replace the plus sign with a minus sign. B to the log base b of x minus log base b of y. There's a property of exponents that says that's the same as b to the log base b of x divided by b to the log base b of y. By this property, once again, this gets replaced by x, this gets replaced by y. So I get x divided by y, and once again, using this property, now replacing x with x divided by y, this is the same as b to the log base b of x divided by y. I've got b to these powers being the same thing. Therefore, the exponents must be the same thing, once again, because b to the x is a one-to-one function. and therefore this property must be true. The final property is that log base b of x to the, say, r power, where r is actually any real number, x has to be positive, but r can be any real number, is r times log base b of x. Once again, take b and raise it to, well, the right-hand side here again, and use a property of exponents. What property should we use? We've got the product of two things there. So I cannot do the same kind of properties I did here, where I separated into a product or a quotient. Instead, I need to do this. I need to effectively take one of those factors outside of the parentheses like this. And the one that makes the most sense is to do it this way, where log base b of x is inside the parentheses and r is outside. You could do it the other way around, but it's not as helpful. This way is helpful because this simplifies to x to the r, and that is the same as b to the log base b of x to the r power. Once again, using this property here, the defining property of the logarithm. And once again, we've got the output of the exponential function b to the x being equal at two possibly different inputs, but that's a one-to-one function. Therefore, the inputs, these exponents, must be the same, and that allows us to say that this property is true. A couple other properties worth mentioning. I already mentioned what the graph of log base b of looks like when b is bigger than 1 here and when b is between 0 and 1 there. Again, this is the main one we're interested in. It has a vertical asymptote at x equals 0. And in fact, it goes down to minus infinity as x approaches 0. The limit as x approaches 0 from the right of log base b of x is minus infinity when we are in the typical case where b is bigger than 1. You can also say the graph is increasing and concave down. You can also say the limit as x goes to infinity of log base b of x is not some constant. This has no horizontal asymptote, just like the exponential function has no vertical asymptote. This is infinity. It grows forever and ever. It gets above any horizontal line no matter how high, though it can grow very, very slowly. So you might have to have a very large value of x before this gets bigger than, for example, 1,000,000. Something else worth mentioning is that log base b of 1 is the number that b must be raised to get 1. Well, that's 0. That's a fundamental property as well. That can be related to this graph. Both of these kinds of graphs have to cross the x-axis at 1. That is their x-intercept. In problem 2, we're going to use what we just learned to evaluate some logarithmic expressions. Part A, log base 27 of 9. What power do we need to raise 27 to get 9? It's got to be a fractional power. Let's see, 27 is a perfect cube, right? 27 is 3 cubed. The cube root of 27 is 3. In other words, 27 to the 1/3 power is 3. We also know that 3 squared is 9. If we combine these two facts, we see that 27 to the 2/3 power is also 9, because by definition, 27 to the 2/3 power is 27 to the 1/3 squared. I'm using a property of exponents there. This is 3 squared, that's 9. All this implies that the question mark is 2/3, and therefore log base 27 of 9 is 2/3. If we want to be sure, you could use a calculator, for example, if you have that available. If I go to my math menu here and go to log base 27 of 9, if you're not feeling very certain about the answer here, we get 0.6 repeating, decimal approximation to 2/3. Okay? So that is the answer for this. But you should be able to figure it out without a calculator. Let's look at part B. Log base 4 of the 6th root of 64. Yikes. All right, let's work it this way. Let's start with the 6th root of 64, which is, well, I'll write it this way first. That's the same as 64 to the 1/6 power. We're trying to figure out what power of 4 will give you this number. Use the fact that 64 itself is a power of 4. 4 squared, 4 to the 2nd power is 16. 16 times 4 is 64. 64 is 4 to the 3rd power. So this becomes 4 to the 3rd to the 1/6, which becomes 4 to the 3/6, which is 1/2 power. 4 to the 1/2 power, which is 2, is the 6th root of 64. Yes, the 6th root of 64 is something simple, so I could replace this with the 2 right away. Anyway, what we see here ultimately is the 1/2 power is what we need to raise 4 to get the 6th root of 64, which is 2. The answer here is 1/2. In the next part, we've got log base 6 of 9 plus log base 6 of 4. It's tempting to think, oh, I guess I have to figure out what should I raise 6 to get 9 and what should I raise 6 to get 4. But those are not simple numbers. In fact, I'll go ahead and use the calculator and see that they're not simple. Go back to my math menu, go to log base. Log base 6 of 9 is not a simple number. It's not clear what that number is. It's probably irrational. Same kind of thing happens with log base 6 of 4. You've got to raise 6 to certain irrational powers to get 9 and 4. It's not a simple relationship. But, so even though each of these numbers individually is something complicated, I can still solve the problem because I can use a property logarithms from problem 1. I've got the sum of two logs with the same base. That's the log of their product. Usually we use this property in the other direction, but here we're using it in this direction. And 9 times 4 is 36. What number do I need to raise 6 to get 36? I need to raise it to the 2nd power. The answer is 2. Again, let's go back here. Log base 6 of 9 is 1.22629, blah, blah, blah. What's log base 6 of 4? Log base 6 of 4 is 0.7737. What happens if I add those two numbers up to some rounding error perhaps? I get 2. Okay, the calculator is giving me exactly 2. It is truly exactly 2 for this problem. Part D is similar, except with a difference of 2 logs instead of a sum. Once again, each individual logarithm is going to be an irrational number, but if I use a property of logs, I got the difference of 2 logs, that's the log of their quotient. And then I simplify it. 72 divided by 9 is 8. What do I need to raise 2 to get 8? I need to raise it to the 3rd power like we saw before. Problem 3 says to use laws of logarithms that we've just been using to rewrite the following expression as a single logarithm. Here we have 3 logarithms. We'd like to write it as just 1 logarithm. All right, so what do we have here? We've got the difference of logs there. We've got a sum of logs there. We have numbers in front of these logs. The first thing we better do is we better bring those numbers up into the powers using the fact that, again, log base b of x to the r power is r times log base b of x. I'm going to use that in reverse here, bring the powers up there. This becomes, keep the log x there first. By the way, just a plain old log means common logarithm, but we could do this problem for any base. And then we bring that 3 up into the power. This becomes minus log of, careful, x cubed plus 1 quantity cubed. Do you need to expand out this binomial? You could, but you don't have to typically in this kind of problem. I'd say just leave it as it is. Then with this next one, bring the 1/4 up into the power. So we have log of 5 minus x to the 6th to the 1/4 power. That could be written as the 4th root of the entire expression, 5 minus x to the 6th. But unless you use the form of the binomial theorem that goes out to infinity with an infinite series, you can't really simplify it anymore. Then you could, as a next step, for example, combine these two things and say this is the log of x over x cubed plus 1 cubed, and then add on this other logarithm. And then as a final step, so there I just use the fact that the difference of 2 logs is the log of their quotient. In the final step, we've got the sum of 2 logs. That's going to be the log of their product. So in the end, we get the log of x times, I can bring the 5 minus x to the 6th all to the 1/4 power up into the numerator if I like this, and leave the denominator as is. And that's about as simple as you could probably go. I wouldn't want to try to do anything more with this. In number 5, we do something similar to number 3, but in reverse. Use laws of logarithms again to rewrite an expression, but now without logarithms of products, quotients, or roots like you see here. Also notice that we have ln as our logarithm. That means log base e, where e is a special number in math. It's about 2.71828. It comes up in a lot of circumstances, especially in calculus. It's as important in math as pi is. It's very, very important. ln is log base e, called the natural logarithm. This kind of problem actually gets at the heart of why logarithms were originally developed, was to be able to compute things like this for various values of x and y. They had to do that kind of thing before they had technology. It's actually still useful today, even with technology. I can think of one example in statistics when you compute what are called maximum likelihood estimators. If you want to look into that, using properties of logarithms in this kind of situation is very helpful. First thing to do here, because of the square root, is write it as a 1/2 power. So we have this entire big fraction, x squared minus 1 over x to the 5th times y to the 4th plus 2 to the 7th. All that is being raised to the 1/2 power. I do that so that I can bring the 1/2 out in front. So I have 1/2 ln of that fraction, x squared minus 1 over x to the 5th times y to the 4th plus 2 all to the 7th. Yeah, don't expand that out. Don't use the binomial theorem there. Then I have the log of a quotient. Write that as the difference of two logs. Keep the 1/2 out in front. Use parentheses so you don't make a mistake. The 1/2 is going to get multiplied by everything. So you would write this. I will multiply the 1/2 back through. That would be a typical kind of thing to do. Also be careful. I'm going to now use the fact that the log of a product is the sum of the logs, and it's important to realize I'm subtracting that entire sum, so I'd want to use an extra set of parentheses. This is a pretty tricky problem, very easy to make a mistake. I'm going to go ahead and multiply the 1/2 back through like this, and then have a 1/2 in front of this, and again use parentheses like this. Because you're ultimately the minus sign is going to have to come through the parentheses, and you're going to get minus signs in both spots. So we have log of a product is the sum of the logs like this. Very easy to make a mistake even in your writing, so I want to be careful that I don't make a mistake. Looks like one more step to do. I can bring the 5 and the 7 out in front here and also distribute the minus 1/2 through. You might wonder, can I bring this 2 out in front? No, because it's not the entire expression that's being raised to the second power. So I have to leave that as is. I get 1/2 ln of x squared minus 1 minus, okay, the minus 1/2 is going through. I bring the 5 down, minus 5/2 ln of x, and also minus, the minus 1/2 goes through over here, the 7 comes down, minus 7/2 ln of y to the 4th plus 2, and I cannot bring that 4 in front either because it's not the entire thing being raised to the 4th power. This is as far as you can go. That is the answer to this question. In number 5, we're back to thinking about inverse functions. F of x is 10 to the x over 2 minus 3, and its inverse function turns out to be 2 times log of x plus 3, where log means log base 10, common logarithm. These are ultimately going to be inverse functions, but part A says first sketch a graph of this function, state the domain, range, and asymptote. It is a transformed version of 10 to the x, and so its graph is going to be similar with some modifications. We're going to explain why it's a one-to-one function, graph its inverse function in the same graph, and state the domain and range and asymptote of the inverse function. Finally, we're going to symbolically confirm that these are inverse functions. I could have mentioned that at the very beginning in the first problem. How to do that is to compose them and see that you get the identity function effectively. So let's go ahead and try to make a nice graph to start with here. Let's use a different color here for the axes. Make it fairly large. So there's my x-axis, there's my y-axis. 10 to the x is going to be a function that's exponential growth for one thing, so it's going to be looking like this. 10 to the x over 2, there's a couple different ways you could think about that. You could think of this as 10 to the 1/2 to the x. In other words, square root of 10 to the x. You could think of it as an exponential function with base square root of 10, which is a little bit bigger than 3. So its graph is going to be pretty similar to 3 to the x, this 10 to the x over 2. But then the minus 3 translates the graph downward, so it's going to have a horizontal asymptote at y equals -3. It's going to get translated down by 3 units. Let's draw a horizontal line there, dash, say, at -3. That's going to be the horizontal asymptote for this function as x goes to minus infinity. The graph's going to look like this. What's the y-intercept? What, for example, is f of 0? That's going to be looking at this formula, 10 to the 0 power minus 3. That's 1 minus 3 is negative 2. So the y-intercept is down at negative 2, right about there. Something about like this is going to be what the graph looks like. You might also wonder what the x-intercept is going to be. Let's not label that, at least right at the moment. It's going to look about like that. I won't bother plotting any more points for the moment. Just trying to get the shape right. As far as its domain goes, domain of f, it's all real numbers, just like the regular exponential function. This r symbol means all real numbers. You could use interval notation if you like, minus infinity to infinity. What is its range? Range of f. What are all the possible outputs? They're all numbers strictly bigger than negative 3, not equal to negative 3. Just like the original exponential function does not reach 0, so this function does not reach negative 3. It does have a limit of negative 3 as x goes to minus infinity. But the range is the open interval from negative 3 to infinity. All y values strictly bigger than negative 3. What is the asymptote? It is this horizontal line, y equals negative 3. That's a horizontal asymptote at y equals negative 3. All right, we're claiming this is the inverse function. Without confirming that symbolically yet, what would its graph look like? I have to take this graph and reflect it across the line y equals x to get the graph of the inverse function. That's y equals x there. Let's make the inverse function blue. Again, it's tricky to do. Again, it might be good to turn your paper so that the y equals x line is going straight up and down. It's still kind of tricky. Things get swapped. The domain of the original function, which was all real numbers, becomes the range of the inverse function, all real numbers. The range of the original function, negative 3 to infinity, becomes the domain of the inverse function. The domain of the inverse function is going to start at x equals negative 3. X is going to have to be bigger than negative 3. And the asymptotes get swapped. The horizontal asymptote for the original function at y equals negative 3 is going to become a vertical asymptote for the inverse function. I should move negative 3 a little bit further over this way, it looks like. It's going to become a vertical asymptote at x equals negative 3 for the inverse function. That's a negative 3 there. Okay, with that information, do your best here. I always find this tricky myself. They're going to touch each other at the same time they cross y equals x. Something about like this is going to be the graph of the inverse function. That's f inverse of x. Oh, this blue pen isn't working very well. 2 log base 10 of x plus 3 is its formula. And yeah, its domain, let's write it in red over here, domain of f inverse is going to be all numbers strictly bigger than negative 3 in interval notation, same as the range of f. You would want to think of the range of f as y values and the domain of f inverse as x values, at least in this picture. The range of f inverse is going to be all real numbers, minus infinity to infinity, and the asymptote is going to be a vertical asymptote. The horizontal asymptote at y equals negative 3 becomes a vertical asymptote at x equals negative 3. Now, part C, symbolically confirm that these are inverse functions. There's a couple ways that could be done. You could think of it in terms of solving for the inverse function in the usual way if you didn't know that, what the inverse function was, and saying that that's a symbolic confirmation. That would be one way to do it. So we have the original function, again, is f of x equals 10 to the x over 2 minus 3 power. To solve for the inverse function, you want to solve this equation for x. So we would add 3 to both sides and get this. Then we take the log base 10, the common logarithm of both sides, like this, and get log of y plus 3. Oops, that's supposed to be a 2. I don't know why I did that again. Equals, take the log base 10 of this, I'll get x over 2. Now multiply both sides by 2 and get x equals 2 log base 10 of y plus 3. Now that, symbolically speaking, is effectively saying we're done. You could think of this as f inverse as a function of y if you like, which is fine actually. You don't have to do the swapping at the end, though it is traditional. But if you do want to make the graphs that you see here, then you would want to do the swapping. I will tell you that in practical problems where the variables have some sort of real-life meaning that you want to stay consistent, you should not do the swapping. And then if I go ahead and do the swapping, that's one way to symbolically confirm that the inverse function is the formula that we showed. But you should also be able to do it with function composition. F compose f inverse of x. The circle means compose. Maybe you haven't had a teacher who showed you that before, but a more common way to write that is f of f inverse of x. F inverse of x is 2 log of x plus 3. If I plug that into f, meaning this function right there in place of x, what do I get? I get 10. The x has to be replaced by this entire thing, 2 log of x plus 3. Don't forget to divide by 2 and then subtract 3. Cancel those 2's. This becomes 10 to the log of x plus 3. Then minus 3 here. And then 10 to the x and log of x are inverse functions. That simplifies to x plus 3. X plus 3 minus 3 simplifies to x in the end. This is the identity function, sometimes written id of x, or maybe 1 of x, where it's not the number 1 really. It's just a symbol for the identity function that maps every number to itself. And technically you should do the other way around as well. F inverse compose f of x is by definition f inverse of f of x. That would be f inverse of 10 to the x over 2 minus 3. I've got to plug that now into this function in place of x. So I get 2 log of, replace x with 10 to the x over 2 minus 3. Don't forget to add 3 like we have the plus 3 here. Those 3's cancel. So we get 2 log base 10 of 10 to the x over 2, log base 10, the common logarithm of x, and 10 to the x are inverse functions, so this simplifies to 2 times x over 2. And we simplify again to x, the identity function, in the end as well. That would be 2 things you could do symbolically to confirm that these are inverse functions. In problem 6, we're doing some equation solving. Find the solution both in exact form and approximate form correct to 2 decimal places. In part A, we start off with an exponential equation where the unknown is in the exponent. To solve such an equation, you want to take the log of both sides. What log? Log base 10, common logarithm, log base e, natural logarithm, or maybe log base 3. Any one of those logarithms will work. Traditionally, in calculus especially, we do resort to typically the natural log, and that's fine. We can do that here. Take the log of both sides, so we get ln of 3 to the x minus 2 equals ln of 20. Use a property of logarithms. Bring this a power down in front. Be sure to use parentheses here so you don't make a mistake. It's the entire thing, x minus 2 times ln of 3 equaling ln of 20. Divide both sides by ln of 3. We're trying to isolate x, so we get x minus 2 equals ln of 20 divided by ln of 3. Therefore, x is ln of 20 divided by ln of 3 plus 2. That's a fine way to write the exact form of the answer. Is it the only way? No. You could, for example, add these fractions by getting a common denominator of natural log of 3. That would give you natural log of 20 plus natural log of 3 times 2 all over natural log of 3. Natural log of 3 times 2, of course, is the same as 2 times natural log of 3, and that 2 could be brought up into the exponent of the 3 to get 3 squared, or 9. 9 times 20 is 180. The top can be simplified to ln of 180 divided by ln of 3. Any one of these is fine for the exact answer. Let's see what it is approximately. ln of 20 divided by ln of 3 is about 2.73. Add 2, I get about 4.73. Let's see if this is the same thing. ln of 180 divided by ln of 3 is approximately the same thing. It is the exact same answer, about 4.73. You might wonder what would happen if I use a different log, like the common logarithm, log. I would get the same answer. Individual numbers are different. Log of 180 is different than ln of 180, and log of 3 is different than ln of 3, but the ratio in the end is the same number. You do get the exact same answer of about 4.73. Graphically, what's going on is if you graph this exponential function, it might look about like this. And if you graph a horizontal line at 20 and figure out where these intersect, it would be at about x is 4.73. That's what's going on graphically. Part B. This is a logarithmic equation. 4 times ln of 5 minus x equaling 3. The unknown is inside a logarithm. You want to exponentiate. Let's divide by 4 first to write ln of 5 minus x equals 3/4. Now let's exponentiate. Since this is a natural logarithm, I might as well use base e. E to the ln of 5 minus x must equal e to the 3/4. These cancel each other out. 5 minus x equals e to the 3/4. Add x to both sides and subtract e to the 3/4. I'd get x is 5 minus e to the 3/4. Of course, 3/4 is 0.75, so I could write that as well. That's an exact form for the answer. What is it approximately? 5 minus e to the 0.75 is about 2.88. That's what that is approximately. What's going on graphically here? The graph of ln of x is increasing in concave up. If I replace x with 5 minus x, what ends up happening is I get a reflection going on, so the graph looks like this. And it does get shifted to the right in the end so that it has a vertical asymptote at x equals 5. The graph of this function looks something like this with a vertical asymptote at 5. If you draw a horizontal line at 3, we have just figured out that they intersect at about x is 2.88 or so. Okay, that would be what's going on graphically there. All right, part C. Now we have both sides involving exponential functions. Sometimes this can be solved by writing both sides as a simple base to different powers, the same base. Here we've got a 10 and an 8. It's not so clear what we would want to do that way. You can just take the log of both sides right away to solve it, whether you can do that simplification or not. ln of 10 to the x plus 4 equals ln of 8 to the 2x. Bring those exponents down in front, so that would become x plus 4 ln of 10 equals 2x ln of 8. A little tricky looking here. We do want to isolate x. It's probably best to distribute the ln of x through here. We've got x's on both sides, and then rearrange after doing so to get x just on one side. So I'll write ln of 10 times x plus 4 ln of 10 equals 2 ln of 8 times x. Subtract this from both sides and also subtract this from both sides. I'd get ln of 10x minus 2 ln of 8 times x equals minus 4 ln of 10. This can be, an x can be factored out of the left side here as ln of 10 minus 2 ln of 8. I could also use properties of logarithms to simplify that. I will probably in the end here. Times x, all times x equals negative 4 ln of 10. A little tricky here. Divide both sides by this. Maybe get rid of that negative sign as well by switching the order of these things. It looks like x can be written as 4 ln of 10 divided by 2 ln of 8 minus ln of 10. This can be simplified a little bit. You can bring this 4 into the exponent. 10 to the 4th is 10,000. The 2 goes into the exponent there to get ln of 64. We've got the difference of two logs. 64 divided by 10 is 6.4, which I could also write as 64 tenths or 32 fifths. There's lots of different ways of writing this. What is all this approximately? ln of 10,000 divided by ln of 6.4. In the end, this looks like it's about 4.96. Now I'm feeling a little shaky here, wondering if I made a mistake. let's check that when I plug this number into both sides, I get the same thing. Let me first add 4 to it, and then take 10 to that number. It's going to be a pretty big number. What would that be? That'd be 915,527,198.7. Let's see if I take 8. If I take the same number again here, natural log of 10,000 divided by natural log of 6.4, multiply it by 2, and then make that the power of 8. Let's see if I get the same thing. Yeah, that looks good. I got the same thing. I'm happy there. All right. So the various ways of writing the exact answer, but approximately speaking, it's about 4.96. Both of these functions are going to be exponential growth functions. I think this is the kind of thing that happens in the end, is that one of them ends up crossing right about there at about 4.96. All right, part D is our last part, and this one's a little extra tricky in a different way. I'll talk about that as we go. We've got a logarithmic equation where I've got two logarithms that are being added, same base, log base 2 of x plus 2 plus log base 2 of x minus 1 equals 2. We do want to exponentiate, but first we want to use the fact that the sum of two logs is going to be the log of their product, like this. That equals 2. Now exponentiate, take 2, since that's the base, and raise it to both sides like this. Do I need to multiply this out? I could. It's probably a good idea, because I think ultimately we're going to have to maybe rearrange and perhaps even use the quadratic formula in the end. I get an x squared minus x plus 2x is plus x. 2 times minus 1 is minus 2. Don't forget about doing it to the right side too. I get 2 squared, which is 4. These two functions cancel each other out. I get x squared plus x minus 2 equaling 4. If I want to use the quadratic formula or factor to solve, I better get the minus 4 on both, subtract 4 from both sides. So I get 0 on one side. I get x squared plus x minus 6 equals 0. And this does factor nicely as x plus 3 times x minus 2 equaling 0. Seemingly giving us two answers, x equals negative 3 and 2. But here's the tricky part. Whenever you do this kind of solving, you can sometimes get what are called extraneous solutions that are not really solutions. They're extra solutions that sort of seemingly popped out of nowhere. You need to check these back in the original function. And it turns out if you plug in negative 3, it doesn't work. Why not? Because if you plug in negative 3 for x in either spot, you get something that's undefined. You can't take the logarithm of a negative number in this class. Turns out if you talk about imaginary and complex numbers, you can, but not for a precalculus class. So negative 3 is not part of the domain. We're not allowed to plug that in. Does 2 work? If I check it with 2, I get log base 2 of 2 plus 2 is 4, plus log base 2 of 2 minus 1 is 1. That is 2 plus 0 is 2. It does work when x is 2. That is the answer, not negative 3. Why did that happen? These things are, two expressions are undefined when x is negative 3. The reason we got a negative 3 seemingly working here in the end is because when I multiply those, I get an expression that is actually positive when x is negative 3. The original individual expressions are not, but this thing is. If you plug in negative 3 here, you get a 9 minus 3 minus 2, that's positive 4, which log base 2 of 4 is 2. I do get the same thing when I've used that property of logarithms, but it doesn't work in the original equation because I have the separate logarithms that are undefined when x equals negative 3. The next two problems are applied problems of the type you typically see in precalculus and calculus, where you need logarithms to solve them. Number says the initial size of a population of bunnies is 1,000. After 4 months, the population has grown a lot. It's tripled to 3,000. Part A, find a formula for the population after t months. So t is time in months. What should the population be? I could call it y. I could call it p for population. I'm trying to find a formula for the population of bunnies as a function of time t in months. And typically these functions are written as the initial value, 1,000, times some base to the t power. However, when you know the doubling time or the half-life, or in this case, the tripling time, it takes 4 months to triple. It's a little quicker, a little easier to write it in this way. We know the tripling time, so I'm going to write a 3 here because multiplying by 3 is the same as tripling, to the t over the tripling time, which is 4. Why does this work? Because when you plug in t equals 4 here, you get 4 over 4 is 1, 3 to the first power is 3, 1,000 times 3 is 3,000. It has been tripled. If this were a doubling time instead, if this were after 4 months it grows to 2,000, I'd want to have 2 to the t over 4, because I'd be focused on doubling time instead of tripling time. If it was an exponential decay quantity, like radioactive decay, and I knew the half-life, I'd have to have 1/2 to the t over the whatever the half-life turns out to be. I'm assuming t is in months here when I write this. T is time in months. It is important to understand our order of operations here. Whenever you plug a number in for t, you compute 3 to the t over 4 first before multiplying by 1,000. Do not multiply by 1,000 first. There's our formula for part A. Part B, find the population after 7 months. That's just evaluating the function at t equals 7. So I get 1,000 times 3 to the 7 over 4 is 1.75. By the way, you can convert this 3 to the t over 4 into other forms. You can convert it into 3 to the 1/4 to the t, so that the base really is the 4th root of 3, 3 to the 0.25, about 1.316 to the t power, meaning 31.6% growth per month for these bunnies. You also could convert this to this form, e to the k to the t, or e to the kt, by figuring out k to be the natural log of this 1.316. ln of that is about 0.27. Approximately e to the 0.274653 times t power would be yet another way to write this function. That corresponds to something called 27.5% continuous growth rate, but I'm not going to explain what that means. Anyway, coming back to solving this problem, we need to raise 3 to the 1.75 power, then multiply by 1,000. After 7 months, the population is about 6839. That's probably too many significant digits. You'd probably for sure want to round to at least 6840, maybe even 6800. If you're talking about, realistically, it should seem like you would have only 2 significant digits. Notice the population did not quite triple again from 3,000 to 9,000. That's because 7 months is 3 months after 4 months, not 4 months after 4 months. F of 8 should be 3,000 times 3. It should be 9,000. Let's try that. If I replace t with 8, well, t with 8, I can do it in my head. 8 over 4 is 2. 3 squared is 9. 1,000 times 9 is 9,000. After yet another 4 months, it would triple again from 3,000 to 9,000. And yes, these formulas do work as well. For example, e to the 0.274653 times 7 power, and then times 1,000 gives us the same answer of 6839 in the end as well. Okay, these formulas work too. Part C, when will the population reach 20,000? So I've got to replace p with 20,000 and solve for t. So now I have to use logarithms. If you have it with base e, it's most natural to use the natural logarithm, but even with base 3, I can use the natural logarithm. Divide both sides by 1,000. I get 20 equals 3 to the t over 4. Take the natural log of both sides. Use properties of logs like this. And then solve for t. I've got to multiply both sides by 4 and divide both sides by natural log of 3. T is going to be 4 natural log of 20 divided by natural log of 3, which could also be written as ln of 20 to the 4th, whatever that is. 10 to the 4th is 10,000. 2 to the 4th is 8. I think it's 80,000. ln of 3, let's just double check that. Let's see what this is approximately. 20 to the 4th. Yeah, no, I was wrong. It's 160,000. Yeah, because 2 to the 4th is 16, not 8. divide by, oh, I got to take the ln of that number, and then divide by ln of 3. T is about 10.9 months is how long it's going to take to get to 20,000 bunnies. Of course, all this is assuming this model is accurate long into the future. It may not be. 10.9 months, does that make sense? After 4 months, it's 3,000. After 8 months, it's 9,000. After 12 months, it would triple again from 9,000 to 27,000. Yes, the answer has got to be between 8 and 12 months, and it is. It's about 10.9 months. Finally, part D, sketch the graph of the population function and relate the graphs to parts B and C. I could do that with my calculator, but let's just do it quickly by hand. This is exponential growth. Got a t-axis and a p-axis. It's a graph that looks like this for my f of t function. I figured out that f of 7, so this is the initial population of 1,000 at t equals 0. F of 7 we found was about 6839. We were wondering how long does it take to reach 20,000? Let's say that's up here. And we found that to be at about t equals 10.9 months. My graph is not to scale on this axis, you can see for sure. I could take the time to make it more carefully, but that's the basic idea. Problem 8 is also about exponential growth, but now for money. How long will it take for an investment to double? So we're talking about doubling time, or we could think about that at least, in value. If the interest rate is 7% per year, compounded quarterly. Here you do need to know how interest is computed. The balance, you might say, B is the balance, is the principal. Sometimes it's called A for amount instead of B for balance, but I'll call it B for balance. It's the principal, P, how much you deposit at the start, times 1 plus the annual interest rate, R, written as a decimal without a percent sign. 7% means 7 per 100, which is 0.07. That's going to be what R is. Divided by the number of compounding periods per year, raised to the power, that is n times t. The number of compounding periods per year times t, assuming t is in years when the interest rate is per year. So n, again, is the number of compounding periods. Quarterly, n is going to be 4. And t is time in years. This is compounding periods per year. T is time in years. And R, again, is the annual interest rate. All right, that's the formula that we need. What is the principal? How much are we depositing? They don't say, because it doesn't matter. I'll just leave it as a P. Replace R with 0.07, replace N with 4. T is unknown. But wait a minute, how can we solve this kind of equation when we got, say, 3 variables, 3 unknowns, it seems like? Well, think about how the problem is phrased. How long, what will T be for the investment to double? For P to grow to 2P, I can replace B with 2P. You can think of B as a variable, but here, if P is fixed, I can replace it with the fixed number 2P. If P were 1,000, this would be a 2,000. If P were 10,000, this would be a 20,000. In the end, it turns out that P is not going to matter. 0.07 divided by 4 is 0.0175. I'm adding 1 to that, so I get 1.0175. The P will not matter. It cancels out. So you're left with 2 equals 1.0175 to the 4t power. We've got to solve for t, use logarithms yet again. ln of 2 equals, using a property of logarithms, 4t ln of 1.0175. In the end, we can write t as ln of 2 divided by 4 ln of 1.0175. I can bring the 4 into the exponent if I like, but I don't have to. This is approximately ln of 2, use parentheses, be careful here, divided by 4 times ln of 1.0175. It's about 9.988 years, close enough to say it's approximately 10 years for the money to double. Now, if you know something called the rule of 70, or a variant of it called the rule of 72, this is not surprising. If your money's growing at 7% per year, the rule of 70 says to approximate the doubling time, take 70 divided by whatever that interest rate is as a 7 here. 7 divided by 70 is 10. Don't take it as a 0.07. The rule 72 says do 72 divided by 7. Looks like 70 divided by 7 is giving us a little closer answer here, but there are some cases where 72 divided by the interest rate works a little bit better. That's just a shortcut that works best when your interest rates are close to 7, 8, 9% per year. Our last problem is related to that tricky thing that happened with extraneous solutions in part D of number 6. We've got two functions here, f and g, that are related. We're going to state the domain of these functions, graph them with technology, and explain the relationships between their graphs. F of x is the sum of two logarithms, ln of x plus 3 plus ln of 2x plus 1. G of x is ln of 2x squared plus 7x plus 3. So let's think about the domains first. For the domain of f, we require both inputs for these two separate logarithms to be positive. X plus 3 to be positive and 2x plus 1 to be positive. We want both of these things to be true. I use the word and. Solving both of those inequalities and keeping the word and in there, we want both x to be bigger than negative 3 and 2x to be bigger than negative 1. In other words, x to be bigger than negative 1/2. We want both of these things to be true. When will they both be true? Draw a picture to help you. A number line. There's negative 3. Here's negative 1/2, say. For this inequality to be true, x has to be to the right of negative 3. And for this other inequality to be true, x has to be to the right of negative 1/2. For them to both be true, this and this, since this blue set is a subset of the red set, it means we want what's in the blue set. That's our condition. Both of these being true is equivalent to x being bigger than negative 1/2. So that's the domain. We could write the domain of f is the interval from negative 1/2 to infinity. For this part over here, we again want the input for this function, 2x squared plus 7x plus 3, to be positive. Require 2x squared plus 7x plus 3 to be positive. How do you solve an inequality like that? You need to factor, and it factors as 2x plus 1 times x plus 3. We've seen these kinds of things before over here, right? We require that to be positive. But that being positive can happen in two ways. Either 2x plus 1 is positive and x plus 3 is positive, or 2x plus 1 is negative and x plus 3 is also negative, because if you have product of two positive numbers is positive and the product of two negative numbers is also positive. These conditions over here are the same as these two conditions over here. This is equivalent to x being bigger than negative 1/2. But what about this one? This condition, 2x plus 1, is equivalent to x being less than negative 1/2. But we also want x to be less than negative 3. In this case, the drawing goes the other way in a sense. Here's negative 3, here's negative 1/2. Everything to the left of negative 3 is there. Everything to the left of negative 1/2 is over here. For both of those things to be true, that's equivalent to saying x is less than negative 3. But in this function here, either this or this can happen. So the domain of g is the union of two separate intervals. It's the interval from -3 to leftward to minus infinity, unioned with the interval from -1/2 to infinity. So the domain is bigger. We can graph them, and I'll graph them with technology. They are the same function where they are both defined, right? Because of properties of logs. We've got log of this product is going to be the sum of the individual logs, which is what this is. F and G will be the same for their common domain, which is going to be this part, but G has a bigger domain overall. So if I graph, let's just graph F first. ln of x plus 3 plus ln of 2x plus 1. Window, I'll go ahead and pick a bigger window. Say -5 to 5 in the x direction. I've already got -5 to 5 in the y direction. We should only see the graph when x is to the right of -1/2 though. There's we see it. Is there a vertical asymptote there? I think so. It's hard to see. The calculator is not really graphing it all the way down there. Maybe we need to plot more points to make sure that happens. Let me go ahead now and go back to my y equals screen and also plug in g of x, ln of 2x squared plus 7x plus 3. I'm going to see a new part to the graph to the left of -3. Here it is. But then when it continues, it redoes this part of the graph. Now you can't tell that for sure, but that is what's happening. These two functions are indeed the exact same function when x is greater than -1/2, but the g function is also defined on a bigger interval. Thanks for watching.